Hi, I'm Paul, KB5MU. I'm here to propose a method for user authentication on amateur satellites. Amateur radio has been using satellites since late 1961, and the technology has been constantly evolving. Except for the recent profusion of single-channel FM satellites, the trend has been towards satellites that are more capable and more useful for actual communications. The next big step forward is to replace the linear transponders with high-performance digital payloads. Open Research Institute has been working on a design for a digital satellite communication system called P4XT that uses many individual digital uplink channels in the 5 GHz microwave band, an onboard multiplexer, and a single broadband DVB-S2 or S2X digital downlink in the 10 GHz microwave band. It will support many simultaneous real-time voice users, as well as a range of capabilities for both higher and lower bandwidth communications. The system is designed for a geostationary orbit, or for a high elliptical orbit. It can also be used terrestrially with a central station or ground sat in a prime location. It's our hope that this system will be affordable, easy to use, and very useful for actual communication between amateurs. Those characteristics will make the system popular with users, supporting a vibrant community of cooperating users. Unfortunately, a system like that may also attract various kinds of misbehavior. It might attract non-amateur users who wish to exploit the utility of the system. It might attract amateur users who disregard the rules and regulations and operating practices recommended by the satellite owner or operator. It might attract users with personal grudges against others, who might seek to use the system for harassment or to deny use of the system to certain people, and so on. These types of misbehavior make the system less pleasant for the majority of cooperating users and can damage the reputation of the system and of the amateur radio and amateur satellite services as a whole. These risks are not imaginary. The amateur satellite service hasn't yet flown a system that was useful enough and easy enough to attract widespread pirate usage, but the U.S. Navy Fleet Satcom satellites from the late 1970s and 1980s have seen extensive pirate use. It was possible to buy the components of a pirate Fleet Satcom terminal at any truck stop in Brazil, and non-military communications could often be heard on the downlink. Because the system was a bent pipe analog transponder, there was little the Navy could do about pirate users operating outside U.S. jurisdiction. For examples of smaller scale abuse by individual users, we need only look to decades of experience with terrestrial FM repeaters. Most have well-behaved user communities, and the occasional misbehavior is readily discouraged by peer pressure or by merely ignoring it. But notoriously, there are other repeaters where misbehavior is quite common and out of control. The repeater owner's only recourse is to turn the system off. We also see misbehavior on HF bands, which can't be turned off. There's just no way to ban persistent abusers. Once we move to a fully digital system, though, it becomes possible to do better. If we're able to identify the origin of every transmission, then misbehaving operators can be held accountable. Just knowing that their identities are public might be enough to discourage most of them. If they persist in misbehaving, the system can deny them access, which eliminates most of their ability to damage the system and the community. Ignoring the thousands of other things that can go wrong with a satellite communication system, space is hard, we will concentrate on problems that can be caused by radio signals on the uplink. We can divide these up into two overlapping classes. Let's call them jammers and abusers. A jammer transmits an especially strong signal with the intent of preventing the desired signals from being received. An abuser, on the other hand, transmits a signal that resembles a desired signal with the intention of using the system in a way not intended by the satellite owner. A pure jammer is a brute force attack aimed at denial of service. There are tricks that can help defend against such attacks, but with enough power, the jammer can always defeat the receiver, no matter how cleverly designed. All radio communication systems have this fundamental vulnerability. A strong enough jammer can prevent communications from working. On the plus side, that strong jammer is pretty easy to detect and locate, so it can eventually be forced to shut down. Even better, there's usually no big incentive to simply jam a whole communication system, unless it's of military or political importance. We can't prevent a jamming attack. We can expect that such attacks on our amateur satellite system will be infrequent, short in duration, limited in effectiveness, and risky for the jammer. At least, we have to hope so. Abuse attacks are another matter. The abusing station is technically very similar to an ordinary user station, at least in terms of basic performance, antenna size, power amplifier, and so on. We want user stations to be affordable, available, and easy to use, which means that the potential abusers also have ready access to the equipment. The potential abuser doesn't need to emit any particularly loud signals, so it can hide among all the ordinary users and evade detection. Perhaps worst of all, in some cases there can be a strong incentive to abuse the system, as in the case of that Navy Fleet Satcom system I described earlier. We have not seen this kind of large-scale abuse on amateur satellites so far, probably because our systems have not reached the threshold of usefulness to attract pirate users. Maybe a P4XT system will cross that threshold. What we have already seen on a large scale is accidental intruders interfering with satellite uplink frequencies. For example, on Oscar 13's Mode B linear transponder, it was pretty common to hear taxi dispatch traffic from Central America. Nothing could be done to reduce this clutter on the downlink. Any kind of regenerating digital transponder solves that problem right away. If a signal doesn't match the kind of signal the satellite is intended to receive, it gets filtered out and cannot accidentally appear on the downlink. So we've narrowed down the problem quite a bit. The only ground stations that can really disrupt the orderly operation of the system, short of brute force jamming, are stations that accurately mimic the characteristics of a normal user uplink. This is similar to the situation we have today on terrestrial FM repeaters. What we need is a way to unambiguously identify the source of any transmission. On digital voice systems based on land mobile technologies like D-Star or DMR, each station is configured to transmit identification automatically, and unidentified transmissions are invalid. But there's nothing stopping an abuser from entering a false identity. We need to add a way to definitely tie each use of a call sign to its actual licensee. This problem is very similar to well-known security issues that arise on the internet, and standard cryptographically secure techniques exist that can be used to solve it. We propose a specific system designed for authentication of users on the uplink to the P4XT digital transponder. The design of this system is constrained by the rules and regulations in the amateur satellite service. Under the United States rules enforced by the Federal Communications Commission, the FCC, no amateur station shall transmit messages encoded for the purpose of obscuring their meaning, except as otherwise provided herein. That is to say, we're not allowed to encrypt the contents of our messages. There is nothing in the FCC rules that prohibits the use of cryptographic techniques for other purposes, such as authenticating amateur uplinks. We just have to be careful not to encrypt any message data. Other countries have similar rules. Some countries may have much stricter rules. It may not be legal to use the proposed system in such countries without a special waiver or rules change. The design is further constrained by the need to be fairly efficient in terms of uplink resources used. We will need to add some authentication data to every uplink transmission, but that overhead needs to be kept pretty small in order to avoid wasting too much uplink bandwidth. It turns out we will also need to occasionally perform an exchange of larger authentication messages between the ground station and the satellite. Those transactions can't occur too often, again, because of efficiency. The rate at which the authentication transactions take place needs to be under the control of the satellite, since the satellite has to handle a large number of simultaneous users and has limited onboard resources for storage and for computation. And we assume, for the purposes of this design, that policy decisions governing uplink authentication are made by the entity that owns or operates the satellite. We hope that most systems can normally be operated in a very relaxed authentication mode, with any licensed amateur radio operator welcome to use the system at any time. We acknowledge that there may be periods of time, such as communications drills or emergencies, when it is desirable to limit the use of a satellite to a predetermined list of users. We have also designed the system to handle the case where the owner maintains a block list of stations that are not currently permitted to use the system. We leave the policy procedures up to the satellite owner to define. We just provide the mechanisms by which the users can be identified in real time so that services can be provided or denied based on policy. Uplink transmissions on the P4XT system are divided up into 40 millisecond frames, mainly because that's what works best for digital voice. Each time the ground station activates its transmitter, the first 40 millisecond frame is devoted to a fixed data pattern called a preamble, designed to be easy for the satellite to recognize and synchronize with. After that one preamble frame, every transmitted frame thereafter consists of a fixed synchronization word that marks the beginning of the frame, a short frame header, and a fixed number of payload bytes. The frame header contains the claimed identity of the ground station, which may be a plain call sign like KB5MU, or a decorated call sign such as KB5MU-15, or actually anything that fits into 9 uppercase letters, digits, and a few punctuation marks. The header also contains other fields pertaining to the P4XT uplink. The header is heavily encoded using a GOLAY code, so it's quite robust and usually received without errors. We extend the frame header by 3 bytes to make room for an authentication token. An authentication token is a meaningless number, not part of any message. The ground station creates the token and inserts it into the uplink frame header. When the satellite wishes to check the authenticity of the uplink, it extracts the token from the frame header and checks it. It's important that the ground station and the satellite can both compute the same token values, and that nobody else can do so. Anybody who is able to come up with a valid token value for another ground station will be able to impersonate that ground station for however long that token value is valid. So we want the token to be valid for only a very short period of time, so that a would-be impersonator can't just intercept the token being transmitted on the uplink and reuse it. Ideally, the token value would change for every frame. So we need a method that allows the ground station to generate an endless stream of unpredictable, random-looking numbers. And we need the satellite to be able to generate exactly the same stream of numbers, and we need it to be practically impossible for anyone else to do the same. We also need to be sure that the sequence of numbers never repeats. Okay, this is a familiar problem, and it's solved by a cryptographic protocol called Time-Based One-Time Password, or TOTP. This is the same thing used by apps like Google Authenticator, or by those little keychain gadgets that display a different 6-digit number every 30 seconds, used for two-factor authentication online. I'm not going to try to explain the math, but here's how it works at a block diagram level. We have a cryptographic computation called a hash function. A hash function takes some number of input bits and generates a fixed number of output bits that depends only on the input bits, but in a complicated way that's practically impossible to reverse. There are standard accepted hash functions used for this kind of purpose, with names like SHA-1 and SHA-256. For input bits, we need at least 2 sources. One source is the date and time. The time changes with every frame, and time is always increasing, so we never get the same input twice. Time is, of course, well known to everybody, so we need an extra input called a shared secret, which is known to the authentic ground station and to the satellite, but not known by anybody else. Where does this magical shared secret come from? It turns out this is also a standard problem. It may surprise you to learn that we can create this shared secret securely over the air. Among other advantages, this means we can replace the shared secret as often as we like. The standard methods for generating a shared secret are called key agreement protocols. The best known key agreement protocol is called Diffie-Hellman, after 2 of its brilliant inventors. If you're at all interested in cool math and aren't familiar with Diffie-Hellman, You should go read up on it. I can't go into the math here. The essence is that each party generates a big random number, which it keeps secret, and then uses it to calculate a second number. The parties then exchange their respective results over the air. Somebody listening in can know both of these second numbers, but does not know the random number for either party. Each party combines the second number they received with the random number they kept secret to generate a third number. And the magic in the math is that the third number works out to be the same for both parties. And that third number is the shared secret. An eavesdropper cannot compute the third number. Neither party can control the contents of the shared secret, so it's not an encrypted message. No meaning has been obscured. Key agreement of this sort uses cryptographic methods, but it is not encryption and not prohibited by the FCC rules. Okay, great. We're getting pretty close to a solution. We have a standard, well-trusted way to generate a shared secret, the Diffie-Hellman key agreement. And we have TOTP, a standard, well-trusted way to use that shared secret to generate one-time tokens for each uplink frame. We're still missing one essential ingredient. How do we know that the ground station is really who it says it is? In other words, how do we link a ground station to a particular real-world identity? Let's back up a minute. What do we mean by a real-world identity? This is really a policy question, so the answer depends on the desires of the satellite owner, and possibly on the choice of authentication mode in use at a given time. During a communications drill or emergency, for example, there may be a very specific list of stations that are authorized to use a satellite, and everybody else is blocked or restricted to certain kinds of use. In that case, what we mean by real-world identity is whatever sort of identification is used on that list. It might be a list of station call signs, but it could just as easily be a set of tactical identifiers that are specific to the served agency or to the specific drill. It's going to depend on what's needed for the situation at hand. For a more general amateur radio scenario, what we mean by real-world identity is almost certainly the amateur radio station call sign held by a specific licensee. Call signs are handy. They're compact and globally unique. Everybody who can legally operate an amateur radio station has a station call sign. In case we need to impose accountability for misbehavior, the call sign is the best way to identify the individual involved, especially when a pattern of misbehavior calls for government involvement. In the United States, the FCC maintains a public database of call signs with the name of the licensee and a mailing address. The mailing address doesn't need to be the licensee's residence or the location of the station or any other particular address, but there is one requirement that does apply. The licensee must be able to receive mail at that address so they can respond to correspondence from the FCC. The mailing address is the main thing that definitely ties the licensee to the license. Can you see where I'm going with this? Somebody has already dealt with these facts and solved the problem of authenticating amateur radio operators. Back around the year 2001, a group of amateurs was working on the problem of digitally authenticating amateur radio contact records. They called their project Trusted QSL, and they got the ARRL, the League, to adopt it for their Logbook of the World project. The Logbook of the World is a way to confirm contacts for awards without physically exchanging QSL cards. Each participating operator uploads the list of contacts they've made, their logbook, and the system searches for matches between uploaded logs. If both ends of a contact have reported matching information in their uploaded logs, both stations get credit for the contact. Some people were worried that a system like this might somehow be less trustworthy than the traditional system of manually checking QSL cards. To reassure those people, the Trusted QSL designers chose to use a powerful cryptographic technique called the Digital Signature Standard to make it practically impossible for a logbook upload to be faked by any third party. Each operator submitting a logbook upload uses special software called TQSL to apply a digital signature to the log file. The signature can only be created by the holder of the call sign used to make the contacts. The validity of the signature can be checked cryptographically, and any alteration to any of the logbook data will invalidate the signature. This trick depends on a method called public key cryptography. The user has a key that is kept secret, referred to as the private key. From the private key, they can derive a second key called the public key. As you might guess from the name, the public key can be shared with everyone without compromising the private key. The key pair can be used in a variety of ways. For digital signatures, the private key is used to compute a number, called the signature, based on the contents of a message to be signed. Since the private key is kept secret, only the holder of the key pair is capable of computing a signature. But through the magic of the math, anyone with a copy of the public key is able to determine whether the signature is valid and was made with the corresponding private key. This gives us a way to tie a message, such as a logbook upload, to a specific private key without knowing the private key. But it still doesn't give us a way to know the real-world identity of the sender. The standard solution to this problem uses a digital document called a certificate. The certificate contains a user's public key and some kind of identification information about that user. In the case of the Logbook of the World, it contains the user's call sign. The certificate itself is then digitally signed by some authority. The signing authority may append its own certificate, which is digitally signed in turn by some higher authority, and so on. At the top of the chain is a certificate from a root authority, which signs itself. This chain of trust relies on the root certificate being well known to all. In order to validate any certificate from anywhere in the chain of trust, you only have to have a trusted copy of the root certificate. Any other certificate in the hierarchy can be validated by checking the signatures up the chain to the root. For the Logbook of the World, there's a single trusted root certificate built into the TQSL software. The League uses that root certificate to sign a working certificate, which is in turn used to sign a certificate for each station that uses Logbook of the World. For this scheme to work, we have to trust that each authority in the chain of trust has done a good job of checking that it only signs authentic certificates. For Logbook of the World, we trust that the League has kept the private key associated with its root certificate secret, and that the League only uses that private key to sign valid working certificates, which it will in turn only use to sign certificates for authentic amateur radio licensees for their legitimate call signs. So how does the League manage to do that? When a U.S. licensee applies for a Logbook of the World certificate, the League looks up their call sign in the FCC database and mails a postcard to the user at their official registered address. The postcard contains login information for a new Logbook of the World account, and the user can download their new certificate and private key from that account. A postcard may not seem like top-flight security at first glance, but remember that being able to receive mail at a particular mailing address is essentially the only fact the FCC knows for sure about a licensee. That postcard gives Logbook of the World the same level of assured authentication as the FCC licensing process itself. For non-US licensees, the League uses a slightly different procedure. The user is required to send in a copy of their license and identification. The League validates the proof visually using some criteria before approving the user's request for a call sign certificate. I don't know what criteria they use. I don't think they've been published. So what does the Logbook of the World have to do with us? Well, we need something exactly like their certificates to tie satellite ground stations to real-world identities, call signs. In fact, we might as well just use the certificates issued by ARRL's Logbook of the World. There is no need to duplicate this mechanism or to build a separate chain of trust. As of this writing, Logbook of the World has 232,000 active certificates, issued to 162,000 users worldwide. That's not every amateur radio operator in the world, not by a long shot, but it probably includes a good percentage of the most active operators. I'm guessing that most people who would be early adopters of a P4XT satellite system already have a certificate. We're not stuck using just one source of certificates either. If the logbook of the world certificates can't be used by everybody for any reason, it wouldn't be too big a deal to establish our own root certificate and issue call sign certificates of our own, in the same way the League does for Logbook of the World. If some entity ever wants to use our P4XT system design outside of the amateur radio services, they could easily establish their own chain of trust based on something other than call signs. The certificate system is more than flexible enough to accommodate any likely use case. So, with the addition of call sign certificates to our key agreement scheme and TOTP frame authentication tokens, we have all the necessary mechanisms to implement user authentication. Let's take a look at how this will work. A user buys or builds a P4XT ground station. As part of the initial setup procedure, they configure the ground station with their call sign certificate from Logbook of the World or some other accepted source. They also configure the ground station with the identity they wish to use on the air, which is probably also their call sign, but could be anything. We call it the claimed identity. Some other configuration is probably needed so the ground station knows the basic parameters of the satellite, such as its downlink frequency and symbol rate. The user then aims the ground station antenna at the satellite and begins to receive the multiplex DVB-S2 or S2X downlink from the satellite. The user can now listen to traffic on the satellite to their heart's content. The downlink contains not just user traffic, but also traffic generated by the satellite itself, including telemetry from the satellite and other information of general interest. It also includes a stream of control messages, including a few that pertain to user authentication. One of these is the auth broadcast message. It contains various parameters that all users need to participate in the authentication protocol. It's transmitted once per second, so that a ground station won't have to wait very long to receive it when first powering up. It contains the date and time to 40 millisecond resolution so that the ground station clock will be in sync with the satellite's clock, which is necessary for the TOTP tokens to match up correctly. It contains a unique identifier for the satellite, just in case we someday have many such satellites in the sky. It contains the public parameters for the Diffie-Hellman key agreement protocol, and it contains two values that define how many frames can be transmitted with the same authentication token. The ground station records these values for later use. When the ground station wishes to transmit, it simply starts the transmit. If it has stored authentication information from a previous session, it can use the old information to fill in authentication tokens for each frame. If it does not have such information, default values are used to create a stream of tokens to use in the meantime. The satellite will receive these frames and evaluate the authentication tokens in them. What it does next will depend on the policy decisions set by the satellite operator. We hope that under normal conditions, the satellite would go ahead and retransmit these frames on the downlink, even if the authentication tokens don't check out. This policy would be the friendliest to users and also minimize the delay in case the user has emergency traffic to transmit. Then, or sometime later, according to satellite policy, the satellite may decide it wants to authenticate the user. This may occur because the user's tokens didn't check out, or just because it's been a while since the user was last authenticated, or for any other reason as dictated by satellite policy. The satellite initiates an authentication transaction by transmitting a directed auth challenge message containing the claimed identity found in the transmission it wishes to authenticate. It also contains an identifier for this authentication transaction, a block of random bits to add security to the transaction, and the satellite's computed value for the Diffie-Hellman key agreement protocol. Notice that we're doing multiple things in parallel here. We're starting the certificate check, but we're also going ahead with the key agreement protocol. The ground station receives this message and matches up the claimed identity field to its own and begins to process the authentication transaction. It formulates a virtual message that will be signed using the secret key associated with its call sign certificate. Notice this virtual message is never actually transmitted by either station. The message echoes back the satellite identifier from the auth broadcast and the claimed identity that was challenged in the directed auth challenge, along with the challenge bits from the message. The ground station supplies its actual identity, its call sign, which must match the identity embedded in its certificate. The ground station also supplies its own computed value for key agreement. and the number of times it intends to repeat authentication tokens within the limits specified in the auth broadcast. The ground station then computes a signature for this virtual message. Now the ground station is ready to reply to the challenge with an auth response message. The auth response contains all the information the satellite doesn't already have, but needs to be able to reconstruct the virtual message: the challenged claimed identity, the actual identity, the challenge identifier, the ground station's computed value for key agreement, and the ground station's intended number of repeats for tokens. The ground station appends a signature it computed for the virtual message and a copy of the ground station's certificate. The satellite is able to validate the certificate based on information contained in the certificate, tracing the chain of trust back to one of the root certificates that the satellite knows about. The certificate also gives the satellite the information it needs to check the signature computed on the virtual message. If everything checks out, the satellite can trust that everything is as it appears to be. The satellite then transmits an auth-ACK message. This message contains both the claimed identity and the actual identity. Notice that means the ground station cannot be truly anonymous, even to other users, even if its claimed identity doesn't have any obvious relationship to its actual identity, since any ground station can receive the auth-ACK message and associate the actual identity with the claimed identity. The auth-ACK message also informs the ground station of the result of its authentication transaction. If everything was accepted, the response is "welcome," and the ground station may continue transmitting. In other cases, the response might be one of these other values. If the ground station is authorized to continue transmitting, then the switchover time from the auth-ACK comes into play. This identifies the specific frame where the ground station is supposed to switch over from using its old or default authentication tokens to using newly computed authentication tokens based on the shared secret agreed upon using the Diffie-Hellman key agreement protocol. So there's no ambiguity. The ground station and the satellite both know exactly what's supposed to go in the authentication token of every frame. If the tokens don't match, the satellite can treat that as evidence that the ground station is not authentic. What it does then depends on policy, but it might well stop retransmitting traffic from that ground station and log an authentication error. It's worth mentioning here that the satellite never retransmits the authentication tokens. They're of no use to other ground stations, and retransmitting them might cause a sneaky side channel for encrypted communications. Once the auth-ACK has been received and the switchover time has arrived, the ground station generates authentication tokens. The date, time, and the shared secret from the Diffie-Hellman key agreement protocol go into a SHA-1 hash function. The hash function computes a 160-bit number. An additional calculation is used to extract a smaller number. In vanilla TOTP, this is the 6-digit passcode the user would read off the hardware token and type in to authenticate a login. For our application, we use this number as the authentication token for a frame or a short sequence of consecutive frames. It would probably be possible to customize this calculation for our purposes and come up with something more efficient than running the entire hash function for every frame. However, when mucking about with cryptographic protocols, it's notoriously easy to make a subtle little mistake and destroy the security of the protocol. Since we're not expert cryptographers, it's safer to just use an existing, well-accepted protocol without modifications, to the extent possible. We presented this poster of our authentication scheme at the hacker convention DEF CON 30 a few weeks ago and asked the hackers for advice. We received some excellent feedback from Kate Gray, W9KAT, pointing out a possible security blunder we had made in modifying TOTP. Using TOTP unmodified is definitely safer, and that's the current plan. Kate also pointed out that with a minor change, we could have the authentication token protect the contents of the frame payload from modification. The token would authenticate not just the sender, but the message itself. We're still evaluating that suggestion. I've shown you a method by which the origin of every uplink transmission can be identified with high assurance. With this protocol in place, as part of the overall system protocol needed to access and use the P4XT satellite, the satellite operator will have the ability to control access to the system and impose accountability on misbehaving users. Except for the need to provide a call sign certificate to the ground station controller, this imposes no burden on the individual user of a ground station. Everything is automatic. The burden on the satellite operator is also light, since the satellite itself can be programmed to implement the designated policy. A prototype implementation of the actual cryptographic calculations used in this design has been written in Python in a Jupyter notebook and benchmarked on a Raspberry Pi. This shows that the computations are not too burdensome for an embedded processor, such as might be used in a typical satellite design. That Jupyter notebook and other documents describing this authentication protocol can be found in our GitHub repository at this URL. This is still an early version of the design. Only the authentication protocol part has been fleshed out to even this level of detail. So there's still time for you to get involved and help out. Your comments and suggestions are sincerely welcomed. We do all our work out in the open, publishing as we go. Not just open source, but open process too. If you're interested in helping out, please visit openresearch.institute and click on Getting Started. You don't have to be an expert, but you might accidentally become one. Thanks for listening. I'll try to answer any questions you may have in the time remaining. Hello. Please type any questions you may have into the chat, and I'll do what I can to answer them. No questions. I'm afraid this is not going to be a very lively Q&A session. I see a question from Gary into AMC. Has this approach been discussed with AMSAT? Not in any kind of detail, no. And thank you, Gary, for proving that the comment system actually is working. Anybody else with questions, please type them in. Comments are welcome too. Jeffrey asks, can you describe the P4XT transponder a bit more as to what it is and what it does? Sure. Um, the P4XT transponder is a fully digital transponder, so uplinks and downlinks are both digital. The downlink is based on a very standard and very state-of-the-art uh, modulation and protocol called DVB S2. And S2X is an extended version of that. This is one big pipe coming down from the satellite with every user's traffic and anything else that the satellite may wish to transmit, all multiplexed into one transmission. So every user can conceptually receive everything. And then on the uplink, individual channels are allocated. The sort of the baseline communication would be voice. So a channel wide enough to carry a high quality digital voice, see my next talk, will be transmitted on the uplink. And then the satellite itself will do the multiplexing automatically, receiving whatever comes up on the uplinks and authenticating them as described here in this talk, and prioritizing them if necessary, and transmitting them on the downlink. Voice is not the only thing it can be used for, of course. It can be used for data or higher speed communications up to some limit, depending on how large the user's ground station is. That is the basic idea. It's intended to be used in a geostationary orbit. May have to compromise and use it in a high orbit, either an elliptical one or a graveyard orbit near geostationary, but not exactly geostationary. And we also intend for it to be usable on the ground. You could put a ground sat or a satellite simulator sort of device on a tower, on a tall building, or a mountaintop if you're so blessed in your area, and do the same sorts of thing. I think that pretty much covers the basics of it. Your next question would probably be when. We don't know. What launch? We don't know. Who's going to pay for it? That's also a problem. Like a lot of ambitious projects, this is going to have to rely on some luck and some wrangling, and we have not yet gotten there. Gary asked a follow-up question. Do you intend to discuss it with them, AMSAT? If AMSAT is involved in the project at some point, we will, of course, discuss it with them. AMSAT has not shown a lot of interest in our project, except negatively. So for the time being, we've not been discussing this with AMSAT. That's all the questions I've seen so far, so type in more. Thank you, Jeffrey. You can join mailing list, Slack channel, watch the GitHub. There are many different ways to keep track of what we're doing. We're completely open and transparent about everything we're doing. That's a goal anyway. That doesn't need to be just responded to here. Thank you, Gary. I'm not seeing any new comments coming in. While we've got a Slack minute here, I will thank Eric KF0AMA, who is serving as host for this presentation. Thanks for your help. Well, what do you think, Gary? Should we, or Eric, should we call it? You're not on screen, so I can't hear you.
Yeah, we can go ahead and call it.
Okay, well, thank you all for your attention. If you have any questions that you didn't get into the chat for whatever reason, get a hold of me. You can find me at openresearch.institute, lots of other places as well. So thanks for your attention, and enjoy the rest of Ham Expo.